Hello, my name is Dragoș Niculescu and I will be presenting Microbenchmarking Documents in the Air on behalf of the team from University Politehnica of Bucharest. This work I did in collaboration with my colleagues Ruse and Costin Carabaș. If we look at the general problem of using maps, we find that most of the benefit we derive from this maps that we use every day is, on one hand, the map itself, and then the second is the annotation, the points of interest, which are curated and placed on that map manually, either crowdsourced or by the owner of the map, as in the case of the Google Maps. Of course, we want to use the same thing indoors. We would like to have points of interest placed on an indoor map, either Cartesian or symbolic. So most of the time, maybe we don't need exact coordinates of a certain location in the building. So room number or building number many times is enough. Now, if we go back to the kind of an old technology like the post-it, this clearly has a context and a obvious location, so we place it either on the lab door or on the fridge door for a reminder. And again, in this case, we don't need the map because the context is natural and location is not needed. Many museums nowadays employ QR codes next to the exhibit so that a user can load that QR code and look up more information about the exhibit. So it's either to navigate the website of the museum or have extra information or extra multimedia about that piece. So in this case, again, we have an annotation of the environment, and the QR code actually indicates the location and the context. But this location, this indication needs to be placed by somebody, needs to be found and scanned with a device. So in all these examples, we see the location-centric usage of documents in which users place and consume documents directly in the environment. So documents are in fact associated with places. This in fact is not a new idea. It was proposed 25 years ago by projects such as sticky notes, sticky documents, GeoNotes, digital graffiti. And in fact, maps are not mandatory for this functionality, so it's very easy for us to use context without an actual map. But if we have the map, then we can answer different queries with or without the map, such as what documents are around me in a radius, or what is the closest document. So the question is how to provide this location-centric services, and in fact we want this indoor, right? If we want to do it outdoor, we already have Google Maps or OpenStreetMap, so it's pretty clear how you can annotate the map and use GPS as a context, as an indication for the location. The question is how to do it indoor, and indoor we have indoor location systems that provide Cartesian or symbolic location. And the problem with this system is that they are kind of labor intensive to set up and to maintain because they depend on the propagation of the Wi-Fi signals indoor. So they can use either Wi-Fi or Bluetooth through a technology called fingerprinting. And in recent years, in this indoor location competition, these are basically positioning systems. They achieved a resolution of 2 to 4 meters, depending on the actual challenges of the building. Now, for the documents in the air, our main idea is to use the signature of the location instead of the actual position. So we want to get rid of this work to achieve positions and use the context. And the context is given by this Wi-Fi fingerprint, BLE fingerprint, or some other sensor readings that we have available on today's smartphones. So the signature, we will be calling it a signature because it can contain many things, but for now we just work with a Wi-Fi fingerprint. The question is what to do with this signature, how to handle this context, and we use a dissimilarity function to compare signatures. So we want a correspondence between this similarity and distance. And the hope is that we don't need to translate this signature to an actual position because this is costly. And we don't need training, as many of these fingerprinting methods require no maintenance and no ownership of the physical space. I can go to an airport, for example, where I don't own the physical space, I don't own the Wi-Fi network, but I can still harvest the signature and save that context on my phone and attach a document to it. On the museum example, the museum of course owns the physical space and the Wi-Fi infrastructure, so it can obviously curate the exhibit and also the documents that are placed, that are attached to those contexts. Now for our case, we propose a very simple API with just two functions, put and get. So we can put a document, we attach it to a signature. So first of all, we harvest a signature from the mobile phone as a collection of signals, Wi-Fi, BLE, cellular, other sensors again. We put the document, which means that the document will go to the server and will be indexed based on its signature, not based on its position, because we don't have and we don't care about position. And then we have a get function, which will try to find documents based on the signature that somebody sees. So the user moves through the building and based on the signature, on the signal condition, radio conditions, it will be able to retrieve a list of documents. The server now can be in the intranet or on the cloud. It depends on the actual application. Now the first question is how to map this dissimilarity to Cartesian space, because in reality we want the system to work with dissimilarity. We want it to work without positions, but in fact people relate to distances in meters, so we want a correspondence between those two, and as of now we are using this dissimilarity based on Brake-Curtis distance, which achieves something like you see in the graph on the right. On the horizontal we have the distance in meters, and on the vertical we have the dissimilarity between 0 and 1. So the idea is that when documents are at a small distance, they have a high similarity or a low dissimilarity, and as you move further away, the dissimilarity increases and approaches 1. So there is no difference between a document placed, let's say, at 10 meters, where probably the dissimilarity is 1, and a document that is placed at 1 kilometer, which will also have a dissimilarity of 1. So for the purpose of our project, we only want to classify documents which are close to the user. And for the rest of the presentation, we'll be using data from several sources. One of them is this one we collected in our building at UPB. And here we collected fingerprint signatures at every 60 centimeters with 2 different phones. Now the collection procedure takes about 3 seconds per scan, and this is a limitation of the Android phones, and I have to underline that these are unmodified phones. What is specific to this building is that we have quite a few access points per scanning location, so it's on median, on average, about 32 access points, but there are at least 20 visible in each spot. This can also be virtual access point, they are not all physical. Now, the first question we need to answer is how to find documents in signal space using that mapping of dissimilarity. So we are now reporting here the dissimilarity that we use. In the table on the right, we see the dissimilarity threshold, and we report how many documents we find in that circle. So, for example, we put the dissimilarity at 0.2. We'll find that 50% of documents are within 60 centimeters of the scanning location, and 95% are in 2.5 meters. So again, if we want to find the document that was placed at that point, then the question is whether we go to that exact location, so the distance will be 0 meters from the scanning point, or we are a little bit away from the scanning position. So let's say 60 centimeters. We are not able to go exactly to that same point, because in usage that's what will happen, or maybe even 1.2 meters or 1.8 meters. So if we don't go to the same location, we still want to find the document. So in all these cases, we look at the CDF, and we see that in each case there is a dissimilarity threshold that we can use that can guarantee 100% retrieval of documents. So documents will always be found, right? If we put the proper threshold. The only question is now how many extra documents will be retrieved if we increase this threshold, and that's what you see in this table. That if you increase the threshold, you'll get some documents which are quite far away. So again, if we are happy with this 0.3 threshold, it's okay. We'll have all the documents, even if we are 1.8 meters away from the scanning, from its true location. But it will happen that we also get points which are 3.8 meters away. So again, for a particular application, these values will have to be tuned properly. Now for the rest of the measurements, we'll be reporting the closest point in the database. So not to deal with this CDF, and it's a bit awkward interpretation all the time. We look at a query point in signal space and in physical space, and we report the distance to the closest point in database. So the closest point will be the closest document that is being returned to the query. And for example, here we see that in 70% of the cases, we report the document at 0 meters. So it's exactly the point, the document that was harvested at that point. And another 30% is a document that is 60 centimeters away. So it's the next best, which is we think is a reasonable performance. I have to emphasize here that in all these measurements, we use one phone for the database, so for placing the document, and a different phone to harvest the signature. So we are not using exactly the same data, because otherwise, we'd probably get 100% accuracy. Now it's interesting to see, if we want to emphasize this difference in devices, how impairments, we want to increase the difference between phones, and we added some extra deviation. So we added a deviation to the readings with the second phone, with the Redmi phone. And this was 1 dBm, 2, 3, 4, 5, and we see that the performance stays about the same. So we still get 60 centimeters away from the query, even if we increase the variation of the phone that is using for the query. So this is good news that we have this graceful degradation. Another impairment that we look at is reducing the density of the access point, because as I mentioned, our building has quite a high density of access points. And so the first box plot is for 0 fraction eliminated, then we eliminate 10%, then 20, 40, And I would say till about 20% APs or maybe 40% APs eliminated, performance is about the same. So there is really not much difference, which shows that in fact the system can work with a much lower density than what we have right now. Another interesting question is that of aging of signatures, and here we use the database from UHI, Universitat Jaume I from Spain, and they basically scanned the same building across a period of 11 months. And in the graph on the left we have the first 20 days in the first month, and then from month to month in the second portion of the graph. And first we plot just the number of access points that are visible, and in the blue we have the absolute number of access points visible at each scan, in fact at each day, but for the entire building, so it's an average for the building. And then in red we plot the cumulative, because what happens in Wi-Fi sometimes, even if you go to the same spot, it's possible that the device will pick some extra access points which were not visible last time you tried that same spot. So it turns out that more access points are available when you look at it in this cumulative fashion. So the question is how, if you place a document at one time, how can you retrieve it at a different time? And here we did cross-validation in time. So here let's say the database was at one date and the query was a different date, how it generally happens in reality. And we get the performance on the left, meaning that again, about 70%, in 70% of the cases, the closest point was the one found in the scan. And we have a few cases which are at 1.5 and 4 meters. But this pertains to how their points are organized on the floor. Another interesting benchmark was on how to perform the scan, and it turns out that it's better to keep the phone at face level and away from the body than to keep it waist level and close to the body. And it's somehow intuitive, because the human body blocks about half of the Wi-Fi signal. So it turns out that this keeping it away and from the body and at face level increases the number of APs. It reduces the power difference when you turn around. And also after you rotate at 90 degrees, it makes less of a difference, which is what you want, because you don't know exactly where you have to be facing when you're doing the scan. And here in the box plot scan, we also test all 4 directions, which is the data that we reported so far. So we average between scanning in 4 directions every 90 degrees. And what is interesting is that in fact you can just choose 2 of these directions. So you can do direction 0 and 2, which is forward and backward. You can do 1 and 3, left and right. You can do 0 and 1, or you can do random 2. So just choose any 2 directions, scan, and perform the average, and the performance will be about the same. So it's what we mentioned, about 60 centimeters. And of course the maximum is around 2 meters. The worst case is when you do random. So if you choose a random direction and you do just 1 scan, then performance is degraded heavily. So to summarize, in documents in the air, we use signatures, not locations. We use Bray-Curtis similarity to make the link between signal space and real space. We have implemented an Android app to collect the signatures and a server to store and index documents, and our performance is similar to what fingerprinting-based positioning system achieve nowadays. What we are doing now, we are trying to enrich the signature with other sources of other sensors that we have on the phone, such as Bluetooth, magnetic sensor, sound. And there are a few interesting directions, such as mapping signature to locations, navigation with signatures. So if we don't have locations, we will still want to do some sort of navigation Hansel and Gretel type of scenario where you find documents and you move along without having the map and without having the actual location. Finally, I left here the GitHub of our project where you can have a look at the data we collected and the code needed to produce the graphs in this presentation. Thank you.